What does continuity mean? So, let's start with this. If I tell you that a function is continuous on a whole set, that just means that at every input in that set, f is continuous at that input. Let's parse that out. So, that means that if a function is continuous, f is continuous on a set U, means that for every p in U, f is continuous at p. What does it mean to be continuous at p?
If that absolute value of x minus p is less than delta, then the absolute value of f of x minus f of g is less than epsilon.
And maybe I'll add like a for all x in U right there. So there's some statement. So let's suppose you were trying to prove some function is continuous. There's some stage where you have to come up with a function called delta, with a quantity called delta. What things is that delta allowed to depend on?
Epsilon and p.
Epsilon and p. And right, of course it depends on epsilon. If you want better control over the difference between f of x and f of p, you need better control over x minus p. But it's also allowed to depend on p. At different places in the domain, you might need different degrees of precision in knowledge about the input to get the same precision about output values. So, on what values can delta depend? Well, it looks like epsilon and p. Here's the idea of uniform continuity. A function is uniformly continuous if this parameter delta, how well you need to control input values, doesn't depend on where you look. A function is uniformly continuous if the value for delta doesn't depend on the value for p. So I'm going to put the definition of continuity over there. And the comment here is delta depends on epsilon and depends on. How would you rewrite this definition so that delta is not allowed to depend on p?
For all epsilon greater than 0, there's this delta greater than 0 and p greater than 0. Or sorry, p and u.
Sorry, I followed you were too quick. For all epsilon bigger than 0.
That's what I said wrong. For all epsilon greater than 0, there exists delta greater than 0 such that for all p and u and for all x and u, if absolute value x minus p is less than delta, then f of x minus f of p is less than epsilon.
Right, that does it, right? Now, if you were going to try to prove a function is uniformly continuous, you'd consider any epsilon bigger than 0. You would then have to come up with a delta. P and U aren't even declared yet, so you can't have delta depending on those things. Then you'd proceed. Yeah, that'll do it. A function is uniformly continuous if, and I'm just going to write the same thing in this line, if for all epsilon bigger than 0, there exists a value for delta bigger than 0, which is independent of the value for p, such that for all x and p in the domain U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. So sure, like that maybe seems compelling that if you have some function, it would be nice to know for absolutely all inputs how closely you need to control those inputs to get some fixed control over outputs. But what theoretical things can you get out of that? So here are some things that will prove about uniformly continuous things that are not true in general. So section 7.5.1 will motivate this definition by exhibiting some continuous functions which fail to have some nice properties. And maybe here I will even like draw pictures of them. There's f of x equals 1 over x, just on the positive numbers. Does that have any properties you would describe as bad? It's got to jump, right? It's got a body class into it. That's like a kind of bad behavior. There's the sine function with a g, the function that just returns +1 if a number is positive, -1 if a number is negative, and I'm not worried about 0 right now. I'll just leave that in the domain. Would you say that second function is continuous on that domain? If I stay in the domain and only change the input a little bit, the output doesn't change. But it has a bad behavior too, right? It's got like a jump. That last function is one that's hard to even like get a good graph of. There's the function sine without a g of 1 over x. Would you say that has kind of a bad behavior at 0? Yeah, I think so. Uniform continuity will avoid those bad behaviors, whatever those bad behaviors are. That's the point of uniform continuity. Just continuity isn't good enough for some things that you really want to happen to happen. And maybe we'll even state them. So here are some nice things that you might want to happen. So here's the theorem we've already proved. Let U be a subset of R. Let F be a function defined on U. Let P be a point that is both in U and a limit point of U. Then the limit as x approaches P of f of x is equal to f of that point. We proved that last time. Not last time, in the past. Limits of functions describe continuity. So here's an observation to make. That means that the limit as x approaches P of f of x exists. Because it has to be equal to f of P. As long as that point P is actually in the domain. Well, what if I have a continuous function and I take a limit point of the domain? Does it always follow that the limit of this continuous function at that limit point exists? And by the way I'm talking, presumably not. And let's just go ahead and see. Well, there are the 2 points that are like limit points of this domain but aren't in the domain. If you were to see that function, I asked you to compute the limit of this function as x approaches 0 or 1. Would you say those limits exist? I think you would. I think the limit as x approaches 0 is 0. The limit as x approaches 1 is 1. So this is a nice function. It has nice behavior. F of x equals 1 over x. I think the limit point of this domain is 0. Would you say the limit as x approaches 0 of this function exists? Depends on how you feel about infinity. I guess you might want to say the limit is infinity, but maybe we haven't even really defined what that means. But that's kind of bad, right? That it diverges. Whether it diverges to infinity or not depends on whether you've made up a definition. The sine function with a g. What would you tell me about the limit of that function as x approaches 0? Well, it kind of wants to be 1, but it kind of wants to be -1. So probably the limit doesn't exist. That's bad. There's a limit point of the domain where the limit definitely doesn't exist. And then there's that last function, the sine of 1 over x. What does that function seem to be getting close to as x gets close to 0? everything between 0 and -1 and 1, I guess. That's probably not the type of behavior you want limits to have. So that limit doesn't exist. Maybe if you want to define like the lim soup as x approaches 0, you could make sense of that. But we won't do this class. So these are all examples of some bad behavior that a function can have. You can have a set u and a continuous function on u and a limit point p of u for which this limit does not exist. So the answer to that question is no, and here are some counterexamples. Do you agree with that? Each of those are continuous functions. 0 is a limit point of the domain of each of those functions. The limit as x approaches 0 of those functions does not exist. Or maybe in the Faust case is infinity. I claim uniform continuity avoids those. And we'll establish that eventually. First, let's address the following. So I guess if uniform continuity is supposed to be like a good condition that'll avoid this bad behavior, and these things have that bad behavior, these functions had better not be uniformly continuous. Let's prove that. So I'm going to focus on these two functions, the sine function with a g and f of x equals 1 over x. We will prove, for one of these, probably not the other, that these functions are continuous but not uniformly continuous. And let's see what people would rather see. So proposition 7.5.3 says that f of x equals 1 over x is continuous away from 0, but is not uniformly continuous. Proposition 7.5.4 says g of x equals sine with a g of x is continuous away from 0, but is not uniformly continuous. Which one should we go through? People want to talk about 1 over x? Maybe people would rather talk about sine with a g. Okay, I think, is that a hand up or just a finger up? Oh, okay. I didn't know if you were just trying to be very subtle.
No.
Okay. Okay. Cool. Let's prove. Let's prove that f of x equals 1 over x is continuous away from 0, but is not uniformly continuous on that same domain. That seem like a goal? Let's start with continuity. We've proven continuity by thinking about sequences. But let's come up with just a self-contained epsilon delta proof of this. So let's prove that this is continuous on that set, but is not uniformly continuous. First, let's prove continuity. So I guess that means that we need to consider anything in the domain, and then any epsilon. Then we need to come up with a delta. Then we need to consider any x in the domain, assume this, get that. That seem like a plan? There's nothing special about the letter P. In fact, I think I'm going to use the letter A instead. So we will consider any A in the domain. Being different from 0 is the same as the absolute value not being 0. I think one assumes that'll be used somewhere in the future. Let's consider any epsilon bigger than 0. Let's let delta be something. We'll figure out what goes there when we know what goes there. We'll wind up with like multiple conditions that we want our delta to do, and that's why it's going to be the minimum of a few things. We'll use different values for delta to get different conditions, and then just take the smallest of all of them. Which, I mean, we've done before, right? We'll come up with a series of delta. We'll consider any x in the domain, assume that the absolute value of x minus a is less than delta. Then, well, there's the sucker we need to show is small. Let's just do what we can with that. What can you tell me about, simplify that, let's see what we get. You just saw that in the wild. What would you want to do to it? Yeah, let's combine those fractions. Get a common denominator. And maybe even do something like that. People agree? Now, what could you tell me about that? Just what seems useful? And let's do something that will walk out to be like a bad thing to do. So like, you could have a natural guess, like I want an epsilon there. So I guess like the intuitive thing is let's set that equal to epsilon and solve for delta. So here is something that will be bad. So delta over absolute x, absolute a equals epsilon. What do you get if you solve that for delta? Well, you get exactly the thing that's written there, right? Like, just move those to the other side. Is anything wrong with just using that as our delta? What's wrong with it? There's an x in there. Delta can't depend on x. Consider any epsilon a in the domain, any epsilon bigger than 0. This delta, this is allowed to depend on a and on epsilon, not on x. That's bad. So, what do we need to do? I guess we need to try to replace this x with a constant up to inequality. We need to find an upper bound, I guess, on a lower bound on how big that x can be, how small that x can be, because it's in a denominator. So let's try to do that. Let's get control over that x in the denominator. If I can show that absolute value of x is bigger than some positive constant, then it's in the denominator, so that inequality will flip. So let's try to do that. And here's the strategy I think I'll use. Absolute value of x is the same as the absolute value of a minus x. Is that correct? Cool. Let's use this to get an inequality. Does the triangle inequality help us here? And let's just see what it tells us. I'll use an erasable pen in case this walks out to the garbage. Right, there's like 2 things you should worry about. Can you do it and should you do it? Like, is it correct and is it helpful? The following will be correct. We'll see if it's helpful. All right, have I just used the subtraction portion of the triangle inequality correctly? Cool. You know what? I want to make this easier on myself. I always get a little bit scared when I use that portion of the triangle inequality. Let's just put something else here. Oh no, that's the version I have to use. Okay. Yeah. Cool. And let's just try to mess around with this. I want this to be bigger than or equal to stuff. Can I make that absolute value of a minus x as small as I need? I could just make it less than delta. And maybe we'll even demand that that delta is less than A in absolute value? So let's require delta be less than the absolute value of A. Then A minus something that's smaller than A will still be positive, so the outer absolute value bars don't actually matter. So I think there's a requirement that I want to put in the list. That is now bigger than or equal to absolute value of A minus delta. Does that feel okay right now? Does that bound on X now look like it's independent of what X is and only depends on A and delta? Nice. I'm going to further simplify a little bit more just to make life easier. And I already have this delta here that I can rely on to make things really, really small. So let's also require, I don't know, just demand that delta be less than absolute value of A over 2. Could I do that? Is absolute value of A over 2 obviously positive? Nice. So that is bigger than or equal to A minus absolute value of A over 2. So far, so good. I just added an extra condition to how small delta is. Let's use that. Now I can say absolute value of 1 over x minus 1 over a is less than delta over absolute value of x, absolute value of a. By the previous line, that is less than, let's say less than or equal to. All these are less than or equal to's right now. Delta over absolute value of a over 2, absolute value of a. Is that now something we could set equal to epsilon and solve? For delta? I think so. And I'm putting a quarter on those equal signs because it's going to be not quite equals at the end. What would you get if you solved that for delta?
Epsilon times the absolute value is
Well, and there's an absolute value and a square, so the absolute value doesn't matter. So this is now less than or equal to 2 times, because that is something bigger than or equal to delta, epsilon a squared over 2 all over a squared. Is that equal to epsilon? Yeah, I mean, of course it is. That's how you got it, that quantity. Nice. So now let's write down the conclusion, then we'll read through the proof again, see if it actually does what we say it does. Thus, for all epsilon, well, for all a in R minus 0, and for all epsilon, there is a delta bigger than 0, namely delta equal to the min of absolute a over 2 and epsilon a squared over 2, such that if the absolute value of x minus a is less than delta, then the absolute value of the difference between the function values is less than epsilon. And let's just see if this proof does that. Do we start by considering anything in the domain? And any epsilon bigger than 0? Do we then come up with a delta? Cool. Do we then assume absolute value of x minus a is less than delta? And do some stuff? and conclude that the difference between the function values is less than epsilon? Neato. That feel pretty okay? And hopefully reasonably familiar. This isn't the first time we've seen like delta needing to be two different things. Whenever you see two different deltas, you just have to take them in. Nice. So there's a proof of continuity. The delta that we came up with, is it independent of A? No. And in fact, it looks like when A gets really, really close to 0, the value for A controls how small delta is, not epsilon. So that's bad. That means as A gets close to 0, even if you want the same control over the output values, you have to use different values for delta. At least according to this proof. But failure to prove something doesn't mean that the thing is false. There might be a better choice of delta. Let's try to prove there isn't one. So, the delta we found depends on A. That's not allowed. That means the proof above does not prove uniform continuity. But a failure to prove a claim is not the same as proving that that claim is false. There might be a better choice of delta. If we want to prove that f of x equals 1 over x is not uniformly continuous, well, let's write down what we need to prove. So let's negate the definition of uniform continuity and see what we need to prove. What do you get when you negate this?
There exists epsilon greater than 0 such that rho delta greater than 0. There exists x in p in u with absolute value of x minus p less than delta. And absolute value f of x from set p greater than or equal to delta.
Cool. People agree? If you want a thing to not be uniformly continuous, then you're saying it is not the case that for every epsilon some stuff happens. So there must exist a counterexample. For that counterexample, there does not exist a delta for which some stuff happens. That must mean for every delta that stuff does not happen. You are saying it is not the case that for every p and x in the domain some stuff happens. There must be a counterexample. The thing you want to show does not happen is an if-then. The negation of an if-then is the assumption is true and the conclusion is false. Feel good? Nice. Groovy. Hopefully, like, that sort of negating, like, you feel more comfortable with now than you did at the beginning of the semester. If that's happened, then, like, I'm pretty happy with that as an outcome of the class. Let's do it then. So what do we need to prove? We need to prove that for some epsilon bigger than 0, for all delta bigger than 0, there are some x and a in the domain, r minus singleton 0, with absolute value of x minus a less than delta, and absolute value of f of x minus f of a bigger than epsilon. I think in order to come up with this proof, I might even rely on looking at a computer-generated graph, because I have to make lots of choices. I need to come up with an epsilon that can't depend on anything. I then need to consider any delta and come up with a value for x and a value for a, which can depend on everything before. So I guess that'll depend on this, like, constant epsilon, but it's just a constant, so, like, they'll depend on delta, though. So let's pull up a computer-generated graph. And this is like, ooh. No, I don't want any of that. I just want that, which you already had in your head. You know what this graph looks like. So can you find me two inputs which are pretty close together, whose output values are not close together. That's what I want. And let's just pick a value for really close. Can you find two inputs that are within 1/2 of each other, or should just within 1 of each other, whose outputs are not within 1 of each other?
Negative 0.5 and 0.5.
Negative 0.5 and 0.5. Negative 0.5, 0.5. Yeah, those output values are pretty far apart. How would you make those input values closer while not having the output values get closer? What if I wanted inputs that were instead like a distance of 1/10 from each other? Well, how about -1/20 and +1/20? Would those do? Are those inputs pretty close to each other? Are the output values like really far away from each other? Cool, I think we might have a plan. So let's suppose I want two inputs. You know what, let's maybe even keep on messing around with it this way. Give me a value for delta. .1. So let's find two inputs. I think the bad thing is going to happen close to 0. Do you see two inputs on this graph that are within 0.1 of each other, whose output values are not close together? Yeah, I guess like 0.05 and -0.05 will do. Let's try that. So, let's see what we can do with this. I guess I don't know what delta is. Let's just muck around and see what happens. We'll figure out epsilon. We'll consider any delta. It looks like negative delta and plus delta do something anyway. We might have to divide some stuff by 2, but that's okay. That's life. And let's just see how close things are getting. So with that choice of x and a, let's compute the absolute value of x minus a. With that choice of x and that choice of a, what do you get? Let's see, it's the absolute value of negative delta minus delta? What is that? Good. Good. Is that what I want to see? No, I want to just see a delta there, but I don't know, like, I should just revise my choice of x and a now, right? What's my new choice of x and a? Just divide by 2. Okay, nice. I also need f of x, absolute value of f of x minus f of p to not be close together. So let's evaluate those differences. And I know that's based on the next page. But like, that's exactly what I'm going to do on the next page. I figure I may as well do it here where everything's on the same page. So, for this trace of x and this trace of a, what can you tell me about the absolute value of f of x minus f of a? And I don't know, I don't feel like doing the simplifying. What is that when you simplify? get rid of all the absolute values, so. Cool. So, and remember, the interesting thing is going to happen when delta is small. Can I make that like really big when delta is small? Cool, so let's do this. So let's let epsilon be equal to 1. I think as long as delta is like less than or equal to 4, this will work. So let's consider any delta bigger than 0. Let's add a without loss of generality. Let's assume delta is less than or equal to 4. Let's let x be negative delta over 2, a be delta over 2. Does it then follow that the absolute value of x minus a is less than delta? Oh wait, does it actually? I think it's exactly delta. That's a problem, isn't it? How do you fix that problem? Divide by more? Instead of dividing by 2, let's divide by 4. Now do I have absolute value of x minus a less than delta? That's good. I now have absolute value of f of x minus f of a. Equal to 8 over delta. Oh. Is that still bigger than or equal to 1? Which is what I want. Oh, cool. Does this look like a proof that just walks? And hopefully also illustrates what failure of uniform continuity means. If you want to prove a function is not uniformly continuous, that must mean that there are two inputs that are really close to each other, for which the corresponding outputs are not really close to each other. Is anyone upset by the thing that I said was without loss of generality? Should we resolve that loss of generality? Because there's just like an extra assumption right now. So maybe this is an aside. What if delta is bigger than or equal to 4? Well, then I think the game is the same. Let's pull up a graph. I want to walk with a delta that is bigger than or equal to 4. I need to find two inputs that are within 4 of each other, for which the corresponding outputs are not within 1 of each other. Somewhere in this picture, do you see two inputs that are within 4 of each other, for which the outputs are not close together? What two inputs are you thinking of? Yeah, I think the same two will do. Where the same two is, I don't know. Let's use those two. Is the absolute value of x minus a less than the choice of delta we've specified? For this choice of x and a, what is f of x? I think it's 2. What's f of a? Wait, negative 2 and 2. Yeah, those are more than 1 away from each other. So we can deal with them without loss of generality. That got a little bit muddled at the end. Does this feel like a proof though? Cool. So there's an example of a failure of uniform continuity. a function is not uniformly continuous if there exist inputs that are really close together whose output values are not really close together. Let's try to prove some things actually are uniformly continuous, though. So, I said I would only address one of these. If you want to talk about sine with a g of x at some point, I have office hours. Maybe mess around with that example over the weekend, and if you can't make it walk, then come see me during my office hour or something on Monday. Let's prove some things are uniformly continuous. So here's a function, f of x equals 3x plus 10. I claim that that is uniformly continuous. Let's try to compose a proof. And the statement of uniform continuity tells me a lot of how the proof should go to begin with. I need to prove something for every epsilon bigger than 0. I then need to come up with a choice of delta. Since I have a formula for this function, I bet I can get a formula for delta. In fact, does anyone just already have a choice for what delta might walk? We'll figure one out. We'll consider any x and a in the domain. We will assume that the absolute value of x minus a is less than delta. We need to show this is less than epsilon, so let's just mess around with what that is. And this is going to feel like really light now. I know what f of x is. It's 3x plus 10. I know what f of a is. It's 3a plus 10. Those parentheses matter. What's that simplify to?
3x times 3x. So 3 times absolute value of x minus a.
Ooh, what do I know about absolute value of x minus a?
Plus delta.
So it seems like a good choice of delta. And let's just see if this is a proof. We consider any epsilon bigger than 0. We then come up with a delta. Does that delta depend only on epsilon? Sure does. We then consider any two things in the domain. We assume the difference is less than delta. We get the output values to be within an epsilon of each other. This is a proof of uniform continuity. And like the simplest possible proof. I think the only one that would be simpler is if this were like a constant function. But constant functions are maybe harder because like you're never actually told what choice of epsilon, what delta to use. So you just have to like write something down because it doesn't matter. Anyway, cool. That argument seemed super easy. Nice. Let's ratchet it up just a little bit. Let's take the function f of x equal to 1 over x. I assert that this is uniformly continuous on the closed interval from 1 to infinity. All right, well, I know how this argument should start, right? Let's consider any epsilon bigger than 0. We will let delta be something we get to pick. We will consider any x and a in the closed interval from 1 to infinity. We will assume that the absolute value of x minus a is less than delta. Then, well, maybe there's a hint there about what's going to happen in the coming lines. Do I know that x is bigger than 1? Or equal to? Yeah, it's in that domain. Same thing with a. Let's see what happens if I use that. F of x minus f of a is 1 over x minus 1 over a. And we simplify that a little bit. It simplifies to
Absolute value of a minus x over absolute value of x times absolute value of a.
nice. And a minus x I know to be less than delta. What would you like to do with this next?
X is greater than or equal to 1 if a is greater than or equal to 1.
So,
Delta over absolute value of x means absolute value of a is less than.
yeah. Or equal to, because these were less than or equal to's. Oh, so what seems like a good choice of delta in this problem? Cool. So, by staying sufficiently far away from that place where something bad happened, that particle asymptote, we got a single choice of delta independent of where we check for continuity. That gives us continuity. So as long as we stayed a little bit away from the bad place, x equals 0 in this case, we got uniform continuity. That seemed good. I think there's one more I have time for. I've got 5 minutes, right? Yeah. Let's do just one more proof of uniform continuity. I know it said I'm only going to do one of them, but I think it makes sense to do a second one of this argument. Let's prove that this is uniformly continuous on the interval from 0 to 1. And let's see, I think there's a recent homomorphic that probably, have you all turned in at this point, that x squared is continuous on the real line? Okay, I haven't graded it yet.
Yeah, I was trying to remember when I did it.
That's fair, that's fair. And maybe you remember there's this ugliness where there's an absolute value of x plus p that you had to deal with, and it was slightly annoying. We won't have to deal with it this time with this added assumption. Let's prove this. So let's consider any epsilon bigger than 0. We'll let delta be something that we get to pick. We'll consider any x and a in the interval from 0 to 1 open because that's what this problem says. We'll assume that the absolute value of x minus a is less than delta. Then, well, absolute value of f of x minus f of a is absolute value of x squared minus a squared. And you all know a bunch of what to do already. What do? Difference of squares. What does that say this is?
Absolute value of x minus a times x plus a.
Cool. And I distributed the absolute values, which is what you surely would have done next. What can you tell me about that?
X minus a is less than delta.
Cool. And in the argument for just continuity, you had to muck around with x plus a and say that's less than 2a plus 1 or something. But we don't have to do that this time. In fact, we can't. That would be a bad thing to do. What's the biggest x could be? What's the biggest a could be?
1.
What's the biggest x plus a could be? In fact, the biggest it could be is slightly dishonest. It's strictly less than. Oh, cool. So what's a good choice of delta? Neato. So maybe let's just read through and check if this is a valid proof of the claim. Does it start with a consider any epsilon bigger than 0? And then it comes up with an explicit choice of delta? That depends only on epsilon? Good. And then considers any two things in the domain? And assumes that those two things are within a delta of each other? And shows that the output values are within an epsilon of each other? There's a proof of uniform continuity. What we will do next time is prove that uniform continuity is good for stuff. For one thing, it preserves the property of Cauchy synthesis. We will show that, use that to show that it preserves the property of limits existing. If you take the limit of a uniformly continuous function at a limit point, that limit will exist. And the last thing we'll do, and we'll see if we get to it, if you take any continuous function on a compact set, this idea of bad stuff can't happen. If you take a continuous function on a closed bounded set, the result will automatically be uniformly continuous. Cool. And I'm at time, right? So as folks are packing up, maybe I'll give you the note that there's nothing explicitly assigned on Canvas for today. That's because this is a 2-day lecture. There is a correspondingly long 2-day assignment posted. Cool.
You said that closed intervals, closed and bounded intervals. You said closed and bounded sets always have uniform continuity. If they have continuity.
If you have yeah, you can't just define any function and it'll be uniformly continuous. Yeah. If you have continuity on a compact set, then you upgrade to uniform continuity for free.
Like if you proved it, proved continuity, like a different method. Otherwise, I guess you could just prove it dependent upon P, and then upgrade it itself at their own.
Yep.
Okay.
Yeah, and that's in fact roughly how the argument will go. We'll say, let's suppose you've already proved continuity. That means that at each choice of P, you get a different choice of delta. Well, that'll give an open couple. At each point, you have a little delta neighborhood where you get a continuity type claim. You can throw out all the finitely many of them. Finite sets have a minimum. Take the smallest of those deltas. But that's like, we'll actually do the proof. I'm just going to be slow so that I need to put my shoes back on.